Welcome back to my channel, Statistics for Applied Linguistics. I'm Dr. Marnie Menegra, and in this video, we will look at an introduction to correlations. So I'm going to explain associated vocabulary with correlations, what correlations are, and the different types of correlations. In other videos, we'll show how to do a correlation in JASP and also linear regressions. So first thing that I want to draw attention to is that there are two or three different types of correlations where they can be either parametric or non-parametric. I've used a similar table with other videos, but Pearson's correlation is the correlation that is most commonly used. And for this correlation, the data is interval or ratio, and we would set this to scale data in JASP. Now, the non-parametric tests, Spearman's correlation and Kendall's tau, in these cases, the data is ordinal or it's in a ranked order. So as an example, let's say if I wanted to see if there was a relationship between the distance of a store from the city center and the amount of money that store was generating on an annual basis. The distance of the store from the center point of the city is going to be your ranked order. You're going to rank those in order, and then you would look at their income or their annual income. So that would be an example of a ranked order for Spearman's or Kendall's tau. Now, what are correlations? We can see a correlation in this graph here. It's a scatter plot graph with a line running through this. And correlations show the relationship or potential relationship between variables. Positive correlations, we can see that both of the variables are increasing. So with a strong positive correlation, the strong positive correlation is where the data points are very close to the line. A weak positive correlation is where the data points are a little bit further away from the line. Now, when it is positive, as the value of X increases, the value of Y increases. Now, we also have negative correlations. With negative correlations, as the value of X is increasing, Y is actually decreasing. So negative correlations, the line is going down. Again, for a strong negative correlation, the points are very close to the line. A weak negative correlation, the points are further away from the line. And no correlation is when we cannot draw a line on the graph. Okay, a linear relationship is when the data appears to follow a line, just like we can see in the strong and weak correlations, both positive and negative. The closer the correlation is to 1 or -1, the stronger the correlation is. So with a strong positive correlation, this would be where the correlation is close to 1. With a strong negative correlation, this would be when the correlation is close to -1, and no correlation is when it would be close to 0. Okay, so if we look at a correlation coefficient, that is the number of the correlation between 0 and 1 or 0 and -1. So when you get the number at the end of doing the correlation in JASP, that number is called the correlation coefficient. Extrapolation. To extrapolate, this is where we're going outside the range of value for what we can expect is going to happen in the future. So here we can see income along the bottom. Now, if I were to find somebody who was making, say, 50,000 in income, we could assume that they're going to be in the top right-hand corner of this graph. Now, extrapolation is different from interpolation. Interpolation is using the line of best fit to estimate the value a variable might take within the range of observed values. So in this case, if I had a different participant or a new number introduced with an income of about 30,000, we could assume it's going to be somewhere close to the line, just above where 30,000 is on the x-axis. So if we go up to the red line here, it's going to be somewhere close to that. Okay, so if we look at the line of best fit, that would be this straight red line through the graph. And that's going to show the trend of the correlation. Linear regression is the value of the straight line. Residuals, this is the vertical distance between each point and the trend line. So if I were going to go to this one of these data points here, the residual is the distance between this data point and the line of best fit. The gradient is the slope, and the intercept is the point where the line crosses the vertical axis. So the intercept here would be close to 14 on the y-axis. Now, one thing we have to be careful of when doing correlations is Simpson's paradox. Simpson's paradox, this is a trend shown in different groups of data. But when the groups are combined, the trend is either altered or it disappears. So let's say I'm looking at a trend between two different groups within a population. And if I combine these groups together, as we can see in the very first graph, it looks like we've got a weaker positive correlation. However, if we recognize that these are two separate groups, as we can see in the second graph, here with these two different groups, we can see that they both have negative correlations if we analyze these groups separately. So that's one thing to keep in mind when looking at correlations is, do you actually have one group or do you have different groups that are performing in different manners? So let's look at Pearson's correlation. There is a link on this slide of how you can learn how to do Pearson's correlation by hand. We used to have to do these by hand, and for the next couple of slides, there are also links on how to do this by hand. You can see the formula just on the left-hand side of the slide. This is the most common correlation with interval or ratio data. Spearman's correlation, this correlation is used when the data is in ranked order, and it cannot be used when there is tied data. So this is typically used when the data is ordinal, such as with a Likert scale, and when there is a monotonic relationship between the variables. As one variable increases or decreases, the other does the same. So here you can see sort of a movement in the first two images. We can see in the first one it's going down, the second one it's going up. If it's non-monotonic, it's kind of going in this U shape. So if you get data such as in the third image, you cannot use Spearman's correlation. If you have tied data, you cannot use Spearman's correlation. Now, Kendall's tau, this correlation is used when the data is in ranked order, first through n, and it's similar to Spearman's, but it kind of does things in a different manner. And the greatest number of inversions, the smaller the coefficient will be. So tau b can actually handle tied ranks. And again, I've got a link for how you can do this by hand. You can also do all three of these correlations in JASP. Now, the one thing to keep in mind with correlations is that a correlation does not imply causation. So when we look at the correlations, one variable is not causing the other to happen. If we're looking for an interaction between variables, this is when we would need to go to an ANOVA. Correlations show a possible relationship and do not indicate that one variable causes the other to happen. And I'm going to show some examples from statology.org on the next few pages. The image on this page is in memes on all these different sites throughout the internet. I cannot find the original author for this meme, but it is this very scary thing when we infer causation from a correlation. So here's the first example. If we collect data for monthly ice cream sales and monthly shark attacks around the United States each year, we would find the two variables are highly correlated. So ice cream sales and shark attacks. Well, are the ice cream sales causing the shark attacks to happen? No, these are just two independent events that are happening at the same time, mainly due to the warm weather in the summer. So one is not causing the other to happen. Another one, if we collect data for the total number of master's degrees issued by universities each year and the total box office revenue generated by year, we would find the two variables are highly correlated. Well, here we're looking at data from 1910 through to 2020. This is over 110 years, or approximately 110 years. What we're also seeing are increases in populations. So we would naturally assume the number of master's degrees issued is going to rise as the population increases, and so does box office revenue in conjunction with inflation. So these are independent events. However, when putting them on a chart together like this, it looks like they have a stronger relationship than they do. Now, the other thing to keep in mind, when you are doing correlations, in order for correlations really to be reliable, you would need to have at least 500 to 1,000 participants, or 500 to 1,000 data points in order to run the correlation. If you have a smaller number, let's say 40 or 50 data points or participants, a correlation is not the best test to use, because we can get an R value for a cluster that is going to look very similar to an R value that will follow a straight line. So the number or the sample size does matter with correlations. Now, this takes us to the end of the introduction to correlations. Thank you so much for watching this video, and I look forward to seeing you in the next video.